A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. The advent calendar may be over, but I am not done with videos for the year yet, because this year we haven't slain a monster yet. Last year's monster that we have slain was Binet's second formula for log gamma. That was absolutely ridiculous, linked down in the description. And I promised last year around that I'm also going to slay the other monster, Binet's first formula for log gamma. And this is what we are going to do today. We are going to derive it from scratch, you could say. It's basically kind of similar to the other Binet's formula for log gamma in the sense that we are going to make use of the very same identity that we have derived several times here on this channel and have used before. This is what you need as prerequisites, and that's basically everything. Link down there to all the videos where I covered these two in the description. This one right here is outright trivial, not gonna cover this anymore. But other than that, yeah, we are going to dive right in, and I hope you are going to enjoy the video. By the way, video has been sponsored by the wonderful people over on Brilliant. More information during the video. And now we are going to dive right in. So this right here, okay, those are the only prerequisites that we are going to need. We have the digamma function of z plus 1 being expressed like this. This has been derived by Gauss at first. Then we have the Fulani expression for log of z being this boy right here, and then we have 1 over 2z being equal to just an exponential function, basically evaluate from 0 to infinity. And the first thing that we are going to do is we are going to subtract log of z and 1 over 2z from digamma of z plus 1. This is the very first thing that we are going to do. So if we take the difference of digamma of z plus 1 and log of z and also 1 over 2z, what we are going to get is basically just a superposition of these three integrals. They all converge in some kind of way, okay, on a certain interval for certain values of z, if they converge, etc. Some conditions, something mathematics. We can actually use the linearity of the integral to bring all of these integrals together under one integral sign. From 0 to infinity, everything integrate with respect to t. So let's do this. All of this gathered together is the integral from 0 to infinity of, okay, this right here is the first part. This is our digamma boy, meaning it's e to the negative t divided by t minus e to the negative tz divided by e to the t minus 1. Next up, we are going to subtract from what we have here this expression, namely minus. What I'm going to do is I'm going to break it up, okay? I'm going to use the additive property of the numerator to turn this into e to the negative t divided by t, and negative turns into positive, so plus e to the negative tz divided by t, and all of this minus e to the negative tz over 2. This is the last part. And all of this integrate with respect to t. Now we can start gathering things together at first. So you're going to notice that e to the negative t over t is going to cancel out here. Other than that, there's not much we can do at this point except for one thing. You're going to notice that e to the negative tz is going to be represented in each and every part of our addition / subtraction here, meaning we can factor it out. Also, what we are going to do is just to make the expression a tiny bit nicer for later, we are going to drag the negative sign to the front, meaning this part right here is going to get a positive sign, this one a negative sign, and this a positive sign, and we are going to add log of z and 1 over 2z on both sides, giving us for now that the above expression is equivalent to saying we have digamma of z plus 1 being equal to, now we got log of z, and then we got plus 1 over 2z, and now minus a mighty integral, I'm going to put it here, minus the integral from 0 to infinity of. Now we are going to factor out e to the negative tz, meaning what we still get is, after factoring out the negative sign, is 1/2 at first, then negative 1 over t, and then plus 1 over e to the t minus 1. All of this multiplied by e to the negative tz, integrate with respect to t. And this is it right now. Now we want to get an expression for log of gamma of z. This is what Binet's formula is called, for log gamma. Meaning, we kind of need to get log of the gamma function out here. I want you guys to remember something very fundamental, namely the digamma function. The digamma function of z plus 1 is the same as the derivative of our gamma function in z of z plus 1 divided by the gamma function of z plus 1. If you take a look at this is actually just the derivative, okay, the derivative in z of log of gamma of z plus 1. I mean, you probably know the property of the logarithm, okay, if we have the logarithm of f of x and we differentiate this with respect to x, this is going to give us by the chain rule the derivative of f divided by f, because 1 over f is the same as the derivative of just log of f if we make use of the chain rule. Meaning, you guys probably guessed it, we are going to integrate this expression right here with respect to z. If we integrate this whole expression that we got here with respect to z, then our derivative operator and our integral operator are basically going to cancel out, giving us an expression for log of gamma of z plus 1. Meaning what we're going to do is we are just going to integrate the whole thing with respect to z, but with upper and lower bounds included. We are going to choose the upper and lower bounds from 1 to z. Z because we want to have a parameterized equation, I mean we want to get an expression for log of gamma of z, so we need z, some kind of variable, as the upper bound, and we are going to use 1 because 1 in the logarithm is going to cancel out very nicely because logarithm of 1 is going to give us 0 overall. Okay, this is just solving an initial value problem using certain initial values which are going to make our life way easier. Meaning if we were to integrate from 1 to z, our digamma of z plus 1 with respect to z. Well, what we are going to get is basically the integral of the differential operator. They are going to cancel out, giving us just the function which was differentiated in itself, logarithm of gamma of z plus 1, but all of this from 1 to z. Now if we plug this into here, we are going to get the logarithm on the one hand of gamma of z plus 1, and on the other hand minus the logarithm of, okay, this is going to give us gamma of 1 plus 1, which is gamma of 2. I want you guys to remember something, and we're going to make use of this fact here. Gamma of z plus 1 is the same as z factorial. By the recursive property of factorial, this is the same as z times z minus 1 factorial. And z minus 1 factorial is the same as gamma of z. This is just something I want you guys to keep in mind. We are going to rewrite this a tiny little bit in a second. But if we use this property here, gamma of 2 is the same as, okay, 2 minus 1 factorial, so 1 factorial, which is the same as 1. Logarithm of 1 is going to cancel out. As mentioned before, we are going to make our life a tiny little bit easier with those initial values. Now we got here, still on the left hand side, dealing a few blows, we still got log of z times gamma of z. Using the logarithmic property, what we are also going to get is that this is log of z plus log of gamma of z. Log of gamma of z is the thing that we want to have at the very end. This is the expression we are looking for. Meaning we are going to solve the whole thing after integrating this side, this right hand side too, with respect to z for log of gamma of z. Meaning before we start integrating this side, let's also add log of z. Subtract log of z on both sides, bringing it to this side over here, and then we are basically good to go to proceed with the process. Meaning, what we're going to do now is we now know that log of gamma of z is the same as. At first, let us subtract log of z on both sides, negative log of z. Now this was the first thing. And now we still need to integrate this whole right hand side with respect to z from 1 to z. Meaning we are going to add the integral from 1 to z of log of z to the whole thing. Integrate with respect to z. Also we are going to integrate 1 over 2z with respect to z. So plus the integral from 1 to z of 1 over 2z, integrate with respect to z. And also what we're going to do is we are going to integrate an integral. Whew, that is funky. Okay, this is going to be a lot of fun. This is the main boy that we're going to play with around during the rest of the video. The rest is very trivial, to be honest. Minus, at first, the integral from 1 to z of the integral from 0 to infinity of, and now we got 1/2 minus 1 over t plus 1 over e to the t minus 1. times e to the negative tz, integrate with respect to t at first on the inside, and the outer integral is integrated with respect to z. Now let us go through these guys here, okay? Let us start with this one. The antiderivative of the logarithm, something you can do in your head, okay? Just using basically integration by parts, integrating the number 1, which is in front of the logarithm. You can see it right now, but 1 times the logarithm is just the logarithm in and of itself. Integrating this and differentiating the logarithm, giving you as an antiderivative z times the natural log of z minus z. All of this from 1 to z. If we plug z into here, obviously we are still going to be left with z times the log of z minus z. And plugging 1 into here, we are going to get 1 times log of 1, which is 0. This is going to cancel out, okay? And since it's the second part of integration, it's negative sign. Negative 1 is going to give us plus 1. Okay, we are done with this. Now, what about this guy here? I mean, we can bring the 1/2 to the front, obviously, just integrating 1 over z, which is very easy, giving us overall 1/2 the natural log of z, integrated from 1 to z, evaluate at 1 to z. Now if we plug 1 into here, it's going to vanish, once again, by the same arguments, log of 1 is 0, and if we plug z into here, we are just going to be left with 1/2 log of z. And this is what we have at the moment. Now, we evaluate these, so the last thing to evaluate is this thing right here. And now we are basically going to make use of the same argument that holds for the Leibniz rule for integration linked down in the description. Instead of differentiating under the integral sign, what we are going to do is we are going to integrate under the integral sign. This is totally doable too. This is nothing special. Integration is basically the same as differentiation. You could say, okay, just the inverse real operator from one another. But you can still integrate under the integral sign. Meaning what we are going to do without any restrictions now, you have to take a look at the various values for z, etc. when everything converges absolutely, blah, blah, blah. A lot of mathematics behind it, but this is not what we are here for at the moment, and we don't have the time for that. We are going to interchange those two, meaning we are going to integrate the integrand that we got right here with respect to z. Now, the only thing that we really need to integrate with respect to z is e to the negative tz, meaning this part right here is going to turn into the integral from 0 to infinity of, now we got something that we don't care about at the moment, plus 1 over e to the t minus 1. And then we are going to integrate from 1 to z e to the negative tz with respect to z, and after that everything with respect to t. Now integrating e to the negative tz with respect to z is very easy, because basically it's just an exponential function, e to the a times z, meaning if we integrate this we need 1 over a, where our a is negative t, so negative e to the negative tz divided by t, all of this evaluate from 1 to z. Yeah, this is basically everything, and now we can start evaluating this from 1 to z. What we are going to get is, at first I would like to bring the negative sign to the front, turning this into a positive sign. Okay, let's do this really quick to get rid of all of these signs that we don't care about at the moment. Other than that, what we still got is, okay, on the one hand, if we plug z into here, it's just going to give us e to the negative tz divided by t. And for the second part of integration, minus plugging a 1 into here is going to give us e to the negative t divided by t. Okay, this is what we got at the moment. And now, basically, what we got is, we got this thing multiplied by this new factor. This right here is an addition of things. Let's distribute this part right here into the first part and distribute this part right here into the second part. And then we are going to use the linearity of the integral to break these two up under the condition that everything converges once again, absolutely, blah, 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 something, something. Pure mathematics. Let us break this up, giving us a final expression. For log of gamma of z at the moment, we are not done yet, we are totally not done yet. There's a lot of things to do still. Being equal to, okay, let us go through everything that we got here. So we got 2 times log of z in some way. But you see, we got log of z, but 1/2 of it, and then we got negative log of z, meaning these two guys that we got right here turn into negative 1/2 log of z. Now, if you take a closer look, we also got z times log of z here. Factoring out log of z is going to give us overall z minus 1/2 log of z. Don't try to lose focus here, okay? There are a lot of factors we need to take care of. quite a bunch of calculating we have to do here. Okay, now we are basically done with this part, we are done with this part, which is also this part, and this one. Then we got negative z, and we got a +1. Okay, just just a stray multiplicative identity, just being in here, just for fun. And other than that, we are going to break up the integral. On the one hand, we are going to get plus the integral from 0 to infinity of 1/2 minus 1 over t plus 1 over e to the t minus 1 e to the negative tz divided by t integrated with respect to t. And on the other hand, we got negative sign to the front, negative the integral from 0 to infinity. Basically what we got here, just without a z. It's not a parameterized integral anymore. This is just a simple integral with respect to t in some way. I'm terribly sorry. Meaning we got 1/2 minus 1 over t plus 1 over e to the t minus 1. All of this multiplied by e to the negative t divided by t integrated with respect to t. And this right here is still not totally done yet. We still have a long ways to go, but this is our basis for getting started, for evaluating basically a final formula for log of gamma, which is very nice for dealing with asymptotic behavior. Just a few things. What we are going to do is we are going to give these two integrals names. This right here is I, but it's a parameterized integral, so I with respect to z. And this guy right here, we are going to call it j. And what we want to do is, since this integral is not parameterized, we are going to try to find the value for our integral j that we got right here. And it needs a lot of manipulation, a lot of nifty things that we need to take care of, but it's definitely doable. And to do so, what we're going to do is we're going to evaluate this whole formula for log gamma of z that we got at this very moment, at z being equal to 1/2 at first. But before we do this, I would like to tell you something about the contents of today's sponsor Prerequisites, who are kind enough to sponsor yet another video here on this channel. Now this right here is obviously high mathematics. Like if you do it very carefully, everything with the conversions is going to be like pure mathematics in a nutshell. It's just absolutely ridiculous. But before you can even get started with evaluating something like the Flammy expression for the log of z, or let it be just the digamma function as the logarithmic derivative of the gamma function, you need to get your basics down at first. And Brain is going to help you with exactly that and their awesome interactive learning concept. Now it doesn't matter what you want to learn, be it analytic number theory or just regular number theory that we are doing here, algebra, physics, computer science, etc. Brian definitely got something up their sleeve for you. And all of their courses and exercises that you can go through on their website can be done by using their interactive learning concept. Interactive in the sense that you can use your hands to get the things done that you want to find out. Just as a little example in number theory, if you want to learn something about prime factorizations, you can go over to the number theory course and take a look at the prime factorization trees, which are going to help you find out something about the prime factorization of the numbers, which is very useful overall, but it doesn't stop there. Go over to the calculus section, take a look at parabolas or hyperbolas, whatever it is. They let you play around with the graphs, play around with the parameters, such that you get a better understanding of the concepts and all the underlying things that you wouldn't normally see when doing just the abstract algebra or whatever on a blackboard. Some things just can be done by calculations. Some intuition can only be learned by doing them for yourselves. And Brilliant is going to be the best source for you to learn something like this. And if this feels like it's something for you, definitely make sure to check out the link at the top of the description, brilliant.org/randommaths. With it, you're going to get free access to a big portion of Brilliant already, but more importantly, the first 100 people to actually make use of the link get 20% of an annual premium subscription, which is a great deal considering how much content they have available on their website already. So definitely make sure to check it out and support the channel this way. And now let's go ahead and get started with ripping that boy apart. Now let us evaluate log of gamma of 1/2. What is that actually? Log of gamma of 1/2. Now gamma of 1/2 is something I have evaluated numerous times here on this channel already. Gamma of 1/2 is the same as negative 1/2 factorial, which is the same as the square root of pi. Now this right here is the square root of pi. Now if we have the square root, this is the same as to the 1/2 power, meaning we can bring the 1/2 to the front, leaving us with 1/2 times the logarithm of pi. That's already cool. We're going to get a logarithm of pi. Very nice. Now if we plug 1/2 into all the other things up here, you're going to see that we get 1/2 minus 1/2. It's going to vanish. So this right here is going to die in the corner. Negative 1/2 plus 1 is going to give us just being equal to 1/2. And then we are going to get plus. Okay, this right here is I of 1/2, obviously. And nothing is going to change here. This one is not parameterized, minus j. So please keep this equation that we got right here in mind. Or if you were to solve this for j, we're going to get that j is the same as just adding this on both sides and subtracting this. J is being equal to 1/2 minus 1/2 log of pi. And then we are going to get plus I 1/2. We're going to need this formula later. But before we can get to this point, what we still need to evaluate is I evaluated at 1/2. And to do this, what we're going to do is we're going to take a look at I of 1/2 first. What is this going to be? I mean, if we plug 1/2 into here, it's just going to be, let me put this as a little note here, negative t over 2. Okay, fairly easy. And we can actually evaluate this. It's rather hard to come up with a solution for yourself. It took me quite a while to get this done, and by quite a while I mean bunch of hours, but we can get there, okay, with a bit of calculations. For this, what we're going to do is we're going to bring our j in the appropriate form at first. We want to bring it into the form of the same exponent that we got right here, of e to the negative t. Meaning what we're going to do for j is we're going to introduce a substitution. So for j, we are going to introduce the substitution that we let t go to t over 2. If we let all the t's go to t over 2, we obviously have e to the negative t over 2 up here. Meaning overall, after doing implicit differentiation, the dt, the differential, turns into dt over 2. Meaning overall, j is thus going to be equal to the integral from obviously 0 to infinity. Nothing is going to change here on the upper and lower bounds. And then we got 1/2 in the integrand minus 1 over t is going to turn into 1 over t over 2, which is the same as 2 over t. And then we got plus 1 over e to the t over 2 minus 1. And all of this times e to the negative t over 2 divided by t over 2, so meaning divided by t, and we are going to bring the 2 up here. But don't forget, our differential turns into dt over 2. Meaning the 2's are going to cancel out in the process, leaving us just with a dt here. And now, next thing we are going to do after we got this new expression for j is we are just going to take a look at I with respect to z and j in a difference. Okay, this is the next thing we are going to do. We are going to take I of z minus j and see where this is going to get us. So I of z minus j is going to be, since we got this boy right here in the appropriate form and we are evaluating our I of z at 1/2. Okay, this is where we are at right now, at this equation, I of 1/2. This is what we want to evaluate. We can, once again, if everything converges, blah, 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 okay, something pure mathematics, bring both of these together into the same integral sign from 0 to infinity. And the good thing is, what we did, we brought this into appropriate form, meaning we got e to the negative t over 2, here it is, over t, as the common factor on everything. And now we are just going to be left with all the things that we got right here, okay, in parentheses now, you could say. And now we are going to go ahead and get started with each and every sum and one after another. So I of 1/2 is the same as 1/2 in here. And then minus j, the first thing of j is just 1/2, so minus 1/2. You're going to see those are going to cancel out. Next up, we are going to get negative 1 over t. And negative is going to turn into plus 2 over t. This right here is the same as 2 times 1 over t minus 1 over t. All of this is going to just turn into 1 over t overall. Okay, this is very nice. And other than that, we got plus 1 over e to the t minus 1, negative 1 over e to the t over 2 minus 1. Integrate with respect to t. What an absolute fucking mess. But it gets better than that, okay? We are still not done yet. We are still not done yet. Papa, please spare us the suspense. Now the next thing that we are going to do is we are going to basically bring those two on the same denominator, and then we're going to add these together. It's actually fairly easy if you consider that we can expand e to the t over 2 minus 1 by e to the t over 2 plus 1, giving us the difference of two squares. So just take a look at that. 1 over e to the t over 2 minus 1 expanded with e to the t over 2 plus 1 divided by e to the t over 2 plus 1. If we expand this right here, you're going to see that this is the same as a minus b times a plus b, giving us just a squared minus b squared. The minus b squared is minus 1 obviously, and then we are going to get as a squared e to the t over 2 squared, giving us e over t. E to the t, giving us overall e to the t over 2. Those are so many e to the t top 2 that I can't do this too much. Divided by e to the t minus 1. Meaning if we were to bring these two guys together that we have right here now, this is what we are looking for, bringing these together, don't forget your negative sign. These are just going to turn into, okay, we got 1 minus 1, okay, getting rid of these two guys, giving us in the numerator e to the t over 2 divided by e to the t minus 1. What a goddamn mess. But let us write everything out, meaning we now know what I, evaluate at 1/2, minus j is. It's actually the same as the integral from 0 to infinity of, and now what we are going to be left with is just 1 over t, and then just the spicy plus e to the t over 2 divided by e to the t minus 1 times e to the negative t over 2 divided by t. Or if we bring the e to the negative t over 2 into here, we are going to have e to the a times e to the negative a is just going to turn into e to the negative e to the 0th power, just being a 1 overall. Meaning this is what we are going to be left with at this very moment. We got I 1/2 minus j being equal to this tiny little integral, which is still fucking annoying to integrate, okay? Because what we have right here is an exponential integral, which is not easy to evaluate in a normal case. But the cool thing is, what we are still looking for to solve for our j, okay, to find out the value of this integral, is to just find out the value of I 1/2. And you know what the good thing is? We just have a, in quotes, simple linear equation to solve by adding j on both sides. Meaning, I 1/2 is the same as j plus our integral that we got right here. Now, if we take a look at j, okay, j is this guy that we have here. We don't want to bring it back to this form that we have right here. This doesn't make any sense for our purposes right now. Why not make use of the original form? After doing substitution, it's an equivalent formulation after all. Meaning what we're going to do is, we are going to bring them together under the same integral sign once again. And then we are going to collect terms. Let us bring the e to the negative t into here and then just factor out the 1 over t on everything, giving us overall an integral from 0 to infinity of, and now we got a huge fucking mess once again. So we got e to the negative t over 2 divided by t plus 1 over e to the t minus 1. This is the first part right here. And now let's add our j to everything. Bringing e to the negative t into here gives us plus e to the negative t divided by 2 minus e to the negative t divided by t plus e to the negative t divided by e to the t minus 1 times dt divided by t. This is where we are at right now. So many godforsaken exponential functions, it's a huge fucking mess. But it gets better in a few minutes. Now the first thing that we're going to do is we're going to bring a bunch of things together. And this right here is not supposed to be a z, this is supposed to be a t. Okay, now it's a tiny little bit better. Now if you take a look at these two guys, you're going to notice that they are going to cancel out in the process. This is already very nice. Now I'm a tiny... Where are they going to get? No, this was supposed to be a 1/2. I'm terribly sorry. Yeah, things like these happen, okay? But I'm a bit sorry for that, but it just happens, okay? Try to do it as I do here on the blackboard, and yeah, it's not an easy matter to do so. So the first thing we are going to do is we are going to bring these two guys together. Obviously, they got the same denominator, meaning we are going to get overall, and is there a negative sign or something missing? I feel like there is something fundamentally wrong right here at this very moment. Let me take a look at this for a second. Okay, I need to figure it out. Oh yeah, I forgot something. I'm terribly sorry for that. There was probably an annotation in the video. What we had here is negative e to the t over 2, meaning we also need a negative sign here. Okay, this was this part up here. We need a negative sign here because we brought the e to the negative t over 2 into here, giving us the negative sign. So if we now collect terms, now we are finally at the point where we can continue. I'm very sorry for that, but this is just something that happens from time to time, and I'm always doing all of these things out of my head. I never take my notes with me when I'm doing a video, so yeah, I'm trying my best here. So the common denominator is going to be e to the t minus 1. Then what we have up here in the numerator is, okay, we get negative, and then we get 1 minus e to the negative t, just factoring out the negative 1 here on both terms, and this is what we are having right now. If we expand this by e to the t, what we are going to get is, on the one hand, we are going to multiply this into here, giving us e to the t minus 1. Okay, this is when we do it this way, meaning this right here is just going to turn into 1, so we get negative e to the negative t. Negative e to the negative t. And now, one thing you're going to notice is we have negative e to the negative t plus e to the negative t over 2. Meaning these two terms together that we got right here are going to turn overall into negative e to the negative t over 2. Okay, now we sorted a bunch of things out. Let us write out what we just scattered. So we got I1/2 is thus the same as the integral from 0 to infinity of, now we get e to the negative t over 2 divided by t. Next up we get, also we get, let me see, e to the negative t over t. We got rid of this part too. Let me see for us. Yeah, no, we didn't get rid of this part yet, but they have the same denominator here too, so we can bring it onto the same basically fraction, so e to the negative t. So we got rid of this part and this part at this very moment. Also we got rid of this part and this part and this part, where all of this is just negative e to the negative t over 2. And all of this integrated with respect to t, and then we still have a factor of 1 over t. This is what I1/2 is at this very moment. But now here comes the hardest part, to integrate this thing. And for this you need to make use of something that we call proof by looking the fuck out of your equation and finally noticing something very nice that has to do with the quotient rule. Let's do this next. So I've written everything out, and now we can continue with the whole spiel. And at first I want you guys to notice something very crucial here. What happens if we put the t into each and every factor that we got right here? I mean, we're going to end up with a t squared here, and we're going to end up with a 2t down here in the denominator. Now when I first saw this, I didn't think much of it, but I want you guys to consider something. When do we get something 1 over t squared in the denominator? Well, obviously when differentiating something of the form 1 over t, something over t. Now exponential functions preserve themselves, meaning if we were to take a look at basically the quotient rule, let us take a look at the quotient rule with respect to t, okay, differentiating with respect to t. Basically what we got up here in the numerator, so e to the negative t over 2 minus e to the negative t, and all of this times t to the negative 1th power, or 1 over t. If we were to differentiate this right here, we are going to get, okay, first part differentiating this right here is going to give us, okay, positive e to the negative t after dragging the negative sign down, minus 1/2 e to the negative t over 2 divided by t. Okay, this is like the first part. And the second part that we are still going to need is, let me see. Now this part right here is going to be preserved, so plus e to the negative t over 2 minus e to the negative t. And then we are going to reduce the exponent of t by 1, so t to the negative 2 is over t squared, and dragging the negative 1 to the front, so negative sign. Okay, that is actually quite curious, because if we make use of the quotient rule, we are going to get exactly what we have right here out on the other side. That is very curious, meaning all that's missing for us to basically extract the quotient rule from this part that we have right here is to kind of get ourselves this part. And how can we get ourselves this part into the integrand? Well, by adding a clever zero, by adding this part and subtracting it right again. And this is exactly what we are going to do, meaning I of 1/2 is the same as the integral from 0 to infinity of, now we are going to get e to the negative t over 2 minus e to the negative t divided by t squared. Now we are going to add this part. Or should I rather say we are going to subtract this part at first, because we are going to see we get negative what we have right here, okay? Meaning, what we are going to do is we are going to subtract this part minus e to the negative t minus 1/2 e to the negative t over 2 divided by t. And now we are going to add it. So plus e to the negative t minus 1/2 e to the negative t over 2 divided by t. And what we still have left is negative e to the negative t divided by 2t. And all of this integrate with respect to t. Now the very cool thing is that this part right here is exactly, if we were to factor out a negative one here, negative the differential in t of e to the negative t over 2 minus e to the negative t, and all of this divided by t. Meaning this right here is actually, and if we break the integral up once again, equal to the integral with a negative sign in front, because we have negative the differential from 0 to infinity of the differential in t of e to the negative t over 2 minus e to the negative t divided by t integrate with respect to t. And shit is going to get real here. I mean, it's a real solution, obviously, but this wasn't an intended pun. Because cool thing is, if we differentiate something with some kind of variable and integrate it over the same variable, it's just a thing in here, just as before, evaluated from 0 to infinity after that, which is very nice. And other than that, we are still left with this part that we got right here. So plus, now the integral from 0 to infinity of, and now we can factor out the 1 over t once again, giving us e to the negative t minus 1/2 e to the negative t over 2. And then we're going to get negative e to the negative t over 2 times dt divided by t. Now on this part, what you're going to notice is that basically we have a minus a over 2 giving us just a over 2 in the process. So let's just get rid of this part right here. Let's put a positive sign here, and this is what we are going to be left with, meaning we got a factor of 1/2 going here, and I'm also going to factor out the negative one, meaning what we are going to be left with after all the evaluation is that I of 1/2 is going to be, okay, as mentioned before, quotient rule turned out very nicely at this point. What we're going to do is we're going to take what we have right here, just the integrand basically, okay, that we differentiated, and evaluate it from 0 to infinity. Don't forget your negative sign, meaning we're going to get negative e to the negative t over 2 minus e to the negative t divided by t, all of this from 0 to infinity. And also, what we have here is bringing the negative sign to the front as well as the 1/2. Negative 1/2 times the integral from 0 to infinity of, and now what we are going to have is e to the negative t minus e to the negative t over 2 divided by t integrate with respect to t. Now this part that we have right here, maybe this seems familiar to you. Think back to the start. Here's a picture. This right here is just the logarithm of, and in our case, 1/2, okay? This is just a Flammy expression for the logarithm. So what we got here ultimately is the natural log of 1/2. So negative 1/2 times the natural log of 1/2. And now what we need to do here is we need to evaluate limits, okay? Because if we plug 0 into here, we get a 0 over 0 situation. If we plug infinity into here, we get a 0 over infinity situation. That ain't good. We are going to do this as a little side note here. So at first, let's let the limit go to infinity, for t to infinity, of this part right here. Now, since we have an undetermined situation, we are going to make use of L'Hopital, meaning the denominator is going to disappear. In the numerator, we are going to get negative 1/2 e to the negative t over 2 and also plus e to the negative t. Letting t go to infinity, you're going to notice e to the negative infinity approaches 0, so we got 0 plus 0. All of this is going to go to 0. Okay, this is very nice. This one is going to vanish. For the second part, limit t approaches 0. What we're going to get is once again the same basically limit. Okay, so the same thing inside of the limit. I don't know what it's called. It's not an integrand or something of that sort, but I think you get the point. E to the negative t over 2 plus e to the negative t. Now, if t approaches 0, we are going to get 1 here. This right here is going to go to 1. And this part right here is going to go e to the negative 0 is just e to the 0, so 1, negative 1/2. 1 minus 1/2 is going to go to 1/2 in the process. Okay, but since it's the second part of integration, negative and negative is going to cancel out, giving us a value for I of 1/2 being equal to, and ultimately, there was a lot of work, and now we are basically done, and there was a wild ride. 1/2. Minus 1/2 log of 1/2. 1/2 is the same as 2 to the negative 1th power. Let's bring the negative 1 to the front, giving us just plus 1/2 log of 2. And this is it. We are basically done. Now we just need to write everything out and then we are good to go. Don't forget j is the same as 1/2 minus 1/2 log of par plus I of 1/2. Meaning our integral j, our final boss in this whole thing is equal to 1/2 minus, and then we are going to get 1/2 log of pi plus I of 1/2, meaning we are going to get plus 1/2, and then we are going to get oh no, let me see for a second. I think we have a sign mistake here. We have a sign mistake somewhere here. In a normal case, what we should get is a negative sign, I believe. So we should get, in the normal case, negative 1/2 log of 2. But I can't put my finger on where we have done a sign mistake here. Let us go through the process once again and let's see where the sign mistake actually happened. So we got this part right here, then we are going to get negative this part e to the t minus e to the negative t set, bringing the negative to the front. I don't see where the sign mistake is right now. There was probably an annotation somewhere and I'm very sorry about that. But in the normal case there should be a 1/2 here and I hope I found a mistake while you're reviewing the video. But things like this happen, okay? At least I'm very honest about things like this. If you have the 1/2 here, what you are going to do or what you are going to see is if we factor out so 1/2 plus 1/2 here is going to give us just 1. Then we are going to get negative 1/2 times log of pi plus log of 2. Now by logarithm properties, this right here is just going to turn into log of 2 pi. And this is basically it. This right here is our j. And now we can just plug our j into our formula for log of gamma of z. And then we are done. Don't forget that we have a negative sign here, okay? We don't want to do any sign mistakes here, giving us overall a final formula for log of gamma of z being equal to z minus 1/2 times the natural log of z, then minus z plus 1. Now we are going to add our I of z to this whole thing, giving us overall, no, our j, we are going to subtract our j from it, so negative 1, and I hope you can see, okay, if we subtract it from it, negative 1, plus 1 minus 1 is going to give us 0, and now we are going to get plus 1/2 log of 2 pi, and all of that plus our I with respect to z, our parameterized integral, plus the integral from 0 to infinity of 1/2 minus 1 over t plus 1 over e to the t minus 1 e to the negative t set divided by t dt. And this right here is the formula for log of gamma of z, and I just thought like covering it in a video at least at some point. I'm very sorry for the goofy sign mistakes that I did here. At least I noticed The first time around I was actually able to recover the negative sign or whatever it was from the fallacious calculation, but here I wasn't able to recover it at this very moment, and I'm a tiny little bit confused about that, and I would like to know what's going on here. But there was definitely some kind of annotation in the video. But never mind that. As mentioned before, at least I'm honest about things like these, and I'm just a human and I'm doing this for fun, and this channel is basically just a library or collection of all the things I'm doing as my personal research, you could say. So yeah, you should be glad that all of this is for free, available on the internet, and I hope you did enjoy what you've seen today. And if you did, why not check out today's sponsor, Prerequisites. They are very nice people with a great website, and they produce very, very good content. So make sure to check it out and support the channel this way. And up until next video, I wish you guys a Flammy day, and please enjoy the last few days of the year. Ciao!